Imagine electricity from a wind farm going into no battery. Instead, it heats a falling stream of sand beyond 1000 degrees Celsius, then pours that material into a giant silo. There is no electrochemical reaction and no lithium. The particles simply become hot, wait behind insulation, and hours later flow through a heat exchanger so a generator can return electricity to the grid. In NREL's enduring concept, resistive heaters raise silica particles toward 1200 degrees Celsius. A moving particle thermal energy storage architecture published by Sandia uses sensible heat, hot and cold storage, an electric heater, a heat exchanger, and a particle lift to form a loop. But granular material transfers heat poorly through tiny contact points, abrades equipment, and must be controlled while extremely hot. So how can electricity become heat inside moving sand, remain stored for hours, then come out fast enough to generate electricity again? The system resembles a bulk material plant, combined with a thermal power station. Its largest components are two insulated silos. One holds particles in the colder state, the other stores them after heating. Cold is relative. Discharged particles may remain far above ambient temperature, but are cooler than the level needed by the selected power cycle. Between the silos is a recirculation path. Cold particles enter an electric heater. Hot particles fall into hot storage. When power is required, a metering valve sends them through a heat exchanger to heat a working gas. The hot, pressurized gas supplies a turbine, or compatible power cycle. Discharged particles collect in cold storage, and a lift returns them to the top. Not every sand is suitable. Researchers evaluate thermal stability, heat capacity, flowability, particle size, resistance to fracture, and cost. NREL compared high-purity silica with manufactured ceramics. Some ceramics performed better, but their added performance did not necessarily justify their much higher price. Silica offers a balance of availability, cost, and temperature stability. The particles store sensible heat. In simplified form, stored energy equals particle mass multiplied by specific heat capacity and temperature change. Capacity can increase through more material, a larger usable temperature range, or both. This separates energy from power. Heater and heat exchanger size largely determine charge and discharge power. Duration can grow by adding particles and silo volume without multiplying the entire power conversion block at the same rate. A stationary bed of rock can retain heat. High power charging and discharging require heat to enter and leave rapidly. A particle touches its neighbors across tiny areas, while gas fills countless gaps. A stationary bed can conduct heat slowly, especially near an exchanger wall. Material beside the surface changes temperature first while the center lags behind. Moving the particles reduces that problem but creates others. Flow may become uneven. A fast channel spends too little time exchanging heat, while a nearly stationary region becomes a dead zone. Particles can arch above an outlet, clog narrow passages, or load equipment unevenly. Every trip through valves, ducts, exchangers, and lifts rubs particles against metal. Particles also collide and break into fragments or dust, a process called attrition. Over many cycles, their size distribution, flow behavior, and thermal performance can change. High temperature intensifies the challenge. Insulation must suppress heat loss. Valves and ducts must tolerate thermal expansion. An indirect exchanger must separate high-pressure working gas from the particle side. The lift must raise bulk material without consuming excessive auxiliary power. Cheap sand does not automatically create a cheap plant. The real problem is making billions of abrasive hot particles exchange heat uniformly, rapidly, and repeatedly, without destroying the machinery around them. The solution is to turn the particles into a controlled stream instead of a passive storage block. During charging, electricity passes through resistance elements and becomes heat. A distributor forms streams or curtains with controlled thickness and velocity. If the layer is too thick or fast, its interior cannot heat sufficiently. If it moves too slowly, surface temperature can rise too far and throughput falls. Gravity then carries hot particles into storage. The silo must limit gas convection, conduction through its walls, and thermal radiation. High-temperature concepts require refractory and insulating layers because ordinary structural material cannot remain directly exposed to extremely hot particles. During discharge, a metering valve controls flow through a heat exchanger. Several architectures exist. In a moving packed bed, particles descend slowly through narrow channels. Working gas follows separate passages, often in the opposite direction. Heat travels from particles through a wall and into the gas. Continuous motion brings fresh particles to the transfer surface. In a fluidized bed, gas agitates particles until the bed behaves more like a boiling liquid. Mixing disrupts stagnant thermal regions. Some arrangements allow direct gas-particle contact. Others keep the power cycle fluid behind a wall. Fluidization can improve transfer but requires pressure work, precise gas distribution, and control against defluidized zones. Counterflow preserves a useful temperature difference along the exchanger. The hottest particles meet gas that is already partly heated, while cooler particles meet cold incoming gas. If the cycle uses supercritical carbon dioxide, the working fluid may be at very high pressure. The exchanger wall must transfer heat while surviving pressure stress, thermal cycling, and particle abrasion. This is why the heat exchanger, rather than the inexpensive storage material, can become one of the system's hardest and most costly components. When surplus electricity is available, particles leave cold storage at a controlled rate. Resistance elements heat them, while sensors track input power, outlet temperature, and flow distribution. Qualified hot particles fall into the hot silo. Electrical energy now exists as increased microscopic motion inside the solid. During storage, valves isolate the two inventories. No chemical reaction must be maintained. The challenge is limiting heat loss through insulation, penetrations, inlets, and outlets. Larger silos can reduce surface area relative to stored volume, although structural loads and thermal stress become more complicated. When the grid requests power, gravity moves hot particles through the exchanger. The working fluid receives heat, enters the power cycle, and drives a generator. Particle temperature, gas temperature, pressure drop, and mass flow guide the controls. Discharged particles fall into cold storage. A bucket elevator, skip hoist, screw conveyor, or another suitable system returns them upward. Electricity used by the lift, gas circulation, compressors, and controls must be subtracted from gross generation. Two efficiencies must remain separate. Resistance heating can convert electricity into heat very efficiently. Returning that heat to electricity requires a heat engine, which faces thermodynamic and practical losses. One Sandia presentation lists approximately 98% heater efficiency, a projected power cycle efficiency of 35 to 60%, and an estimated commercial electricity to electricity round-trip efficiency of 33 to 57%. Those are projected ranges for the described architecture, not measured performance for every particle system. This technology is not intended to beat lithium-ion batteries in every role. In exchange for lower round-trip efficiency, it targets inexpensive storage material, high temperature, and long duration. After the power block is installed, additional duration can depend mainly on more particles and larger storage, rather than duplicating every power conversion component. Moving particle thermal energy storage works because it separates three jobs. The heater controls how quickly electricity becomes heat. Particle mass and insulated storage determine capacity and duration. The heat exchanger and power cycle determine discharge power and how much energy returns as electricity. Particles must move to bring fresh hot material to the transfer surface. Yet that motion creates abrasion, uneven flow, auxiliary loads, and a control problem. The complete loop is the answer. Resistance heating charges the particles. Gravity fills hot storage. The exchanger heats a working fluid. The generator returns electricity, and the lift recirculates the cooled particles. This is not merely a silo of hot sand. It is a rechargeable thermal power plant in which the cheapest material forces the surrounding machinery to become the most precise.